Hello there, this is Ms. Page. In this lesson, we are going to look at how to graph exponential decay functions using our knowledge of transformations. We're also going to look at how to identify some key characteristics of the function, either using the function itself or the graph of the function. So one thing that we have previously learned that we will be applying today is that when we look at a function such as here, g of x equals 2 to the power of negative x, and compare it to f of x equals 2 to the x, which we refer to, which we think of as a parent function, that this negative on the x here, which represents a -1, that is our 1 over b parameter. And the reciprocal of that, b, which also is -1, since -1 is its own reciprocal, tells us whether we have horizontal stretches, compressions, and y-axis reflection. So since it's negative, we have a y-axis reflection. The absolute value of b, which is the absolute value of -1, which is 1, tells us there's no stretch, no compression in the horizontal direction here. The thing that I want to point out is this y-axis reflection, because g of x is a model or is a function that represents exponential decay, and f of x represents growth. So if you look at those two, the only difference between them is that the decay function is a reflection across the y-axis of the growth function, which uses our powers of 2 that we use to help us graph growth functions in the previous lesson. So what we will do to help us graph decay, and this will simplify the process, is we'll use those same points, the points from f of x equals 2 to the x, which are those powers of 2, using x values that are the integers from -2 to 3. And then the y's correspond to the powers of 2 that we get. So we'd have 1/2, we'd have 1, we'd have 2 to the first, which is 2, 2 squared, which is 4, 2 cubed, which is 8. And what we'll do is we'll take these and we will reflect them across the y-axis. And then if we have any stretch or compression or translations, we will do that afterwards. And that will allow us to graph our decay functions. All right, so here, this is just reminding us of some of the same stuff that we talked about before. An exponential function in general, this is its structure, where we have our a, c is like that -1, that's our 1 over b, but we don't use that here because it's traditional to use b as the base value of an exponential function, so they're not the same. And so we don't want to confuse the matter. And then what we also know is for any exponential function, growth or decay, its base has to be positive, greater than 0, but the base cannot be 1. We have, remember, a horizontal asymptote for all of these equations that is y equals k, our k parameter found there. And when we graph an exponential function, we'll graph that horizontal asymptote. We'll graph as many of the key points as we can, including the y-intercept, if it fits onto our graph. And we'll either graph the 0 or estimate the 0 with our curve when it's reasonable. And then, of course, we have the 2 pieces of end behavior that we include, which means basically stick those arrows on the ends when you're graphing by hand. All right, here's what can make decay functions a little bit more challenging than growth, is that we do have a couple different primary ways to write a decay function. So here we're looking at the 2 different ways. The first way is to write the function with a base that is actually greater than 1, which makes it look like growth. And this goes back to that prior knowledge problem, like y equals 2 to the negative x power. That actually is decay. The base here, if we change x to a positive x, this would correspond to, y equals 2 to the negative first to the x, and 2 to the negative first is our base of 1/2, which is the actual base value of a decay being between 0 and 1. So we have to be on the lookout for that. We can't just look at the base value. We also have to consider, is x positive or negative? Because if it's negative, then this number is actually its reciprocal for the base. So if we have, if you have like 1/2 to a positive x, then you've got decay also. So this is one way to write this decay function, and this is the other way to write this decay function, 2 to the negative x and 1/2 to the positive x. All right, so this is showing the decay model, but this would give us new points to learn. So I'm not going to use the points in this table. I'm going to use the points from 2 to the x and then apply that y-axis reflection in these problems. Those of you who might be really good at memorizing multiple sets of points, then you might prefer to just start with these points shown here and not do the y-axis reflection. So here's showing again what I've been talking about with the difference between growth, which is this increasing function, and decay, which is a decreasing function, shown written both ways for 2 to the x and 2 to the negative x, or 1/2 to the x. So you'll notice that their relationship to each other is they differ by a y-axis reflection. So this point reflects over here. That's that one. This point reflects over there. That's that one, and so on. All right, so let's take a look at graphing this decay function. This one is shown with the base of 1/2. So that means we're going to use those powers of 2, and we're going to apply a y-axis reflection to create a decay model, which would have a base of this 1/2. The other things that we have, of course, we have a k value here of -2. And that means, of course, that we also move down to, remember, that also gives us the number for our horizontal asymptote, which would start with y equals. So we have y equals -2 for that horizontal asymptote. The opposite of this -2 would be our h. So our h is +2, which means we have a translation to the right as well. All right, because this is decay, remember, we are also going to do a y-axis reflection because the points I'm going to use are going to come from y equals 2 to the x, which is our growth function. Points, not pointy. So remember, those points would be our -2 1/4. So continuing with our key points from 2 to the x, our growth function. So what I'm going to do with each of those is a y-axis reflection, and then I'll do my translations right and down. And as far as our key features are concerned, too, we've talked about the domain for all exponential functions will be the set of all real numbers, because exponential functions are continuous functions. No breaks in them as the curve moves from left to right. So here we're looking at, for domain, the set of all x's such that -infinity is less than x and x is less than infinity, and our interval notation. Y-intercept, we've talked about, we can calculate the y-intercept for any function using the understanding that any point on the y-axis has an x value of 0. So I'm going to do that math over here. So I'm really looking at g of 0, which would be 1/2 to the power of 0 minus 2, and then followed by a -2. So here, this is 1/2 to the power of -2. So remember, negative exponents do not mean negative numbers. They mean reciprocal powers. Reciprocal powers, meaning that the reciprocal of this 1/2 to the positive exponent is what this really represents. So this actually is 2 squared, which is 4, and then the 4 minus that 2 there gives us a y-intercept, y-coordinate of 2. All right, so we'll leave again range and in behavior until we're done with the graph. So taking a look at my situation, remember all of these points from -2 to 3, they're going to reflect, which means that their x's are going to change signs. So -2 is going to become a +2, and then it's going to move to the right 2 units. So it's going to move over to 4. So I need to make sure that I can get over to 4 on the x-axis. And so I can easily do that. So I'm going to put my y-axis over here. And then try to get that a little better. So the other thing is, where should I put my x-axis? So remember that for an exponential function, unless there is a x-axis reflection, all of the points will be above the horizontal asymptote. So our horizontal asymptote's at y equals -2. So all of our points will be above that because we do not have an x-axis reflection. So I'm going to put my x-axis right here. And again, I'm going to put some numbers on this to help with the accuracy of graphing. Make sure my eyes see things and put things in the right spots. And then remember that I want a dashed line for my asymptote at y equals -2. All right, so now I'm going to begin transforming my points. So I'm going to start with 3, 8, like I did with the previous one, just because I like to start there. So 3, 8, I'm going to do a y-axis reflection. So it flips over here to -3, 8, and then I'm going to translate it. So it translates right 2, 1, 2, and down 2, down 2. So it ends up here at -1, 6. 2, 4 is my next one. So it reflects across the y-axis to -2, 4, and then it translates right 2 and down 2. It ends up at 0, 2. Notice that's my y-intercept, and it corresponds to my math calculation. So that's a good sign that things are going well so far. 1, 2, reflect across y, then translate right 2, down 2. That's actually our 0 because that's on the x-axis. And then 0, 1 doesn't move when we do a reflection. It's what we call its own reflection because it's on the y-axis, but it does still translate right 2, down 2. -1, 1/2. Since it's to the left of the y-axis, the reflection puts it on the right side, and then at +1, 1/2, and then it translates right 2, down 2, and ends up at 3, -1 1/2. And then my little -2, 1/4 flips to the right side, translates right, translates down, and ends up, as I would expect, real close to my asymptote. So now I'm going to draw my curve as best I can with making it smooth. Didn't do too bad this time. So that completes my curve, my g of x function. So now I'm going to go back to my key features. I still have to do my range. So here I can see my range, my y values for my points are all above or greater than the y value of the asymptote, which is -2. So now we have a range of the set of all y's such that y is greater than -2. Interval notation, remember, for y, least to greatest is bottom to top. So we start at the -2 and end up at positive infinity. And behavior, our left end, we can see that's as x goes to -infinity, because we're heading to the left. It's heading up. So that end, our g of x values are going to infinity. For our right end, it's the one that's getting closer to the asymptote, but as it heads to the right, x is still going to positive infinity as we go to the right. So as x goes to infinity, it's our y values that are going to the y of the asymptote. And so the asymptote has a y value of -2. So our g of x values on that end are heading towards a y value of -2. All right, that finishes up that problem. Let's take a look at this one. So here, this one is the way it is written is quite honestly a little tricky. We're going to rewrite it because notice the exponent is a negative x minus 3. And so there are a couple of things going on. We have to recognize this is decay because x is negative and our base is 2. So that's going to change our 2 into a 1/2. However, the structure to get the correct h value for our horizontal translation needs to be x minus h in parentheses. So that means that this -1 here, we're going to want to factor out of negative x minus 3. The other thing is, remember, we talked about this in the previous lesson. This negative in front of the 2 does not mean -2 is to that exponent. We'd have to put it in parentheses if we wanted the negative included. And remember also, exponential functions must have positive bases. We're not allowed to have a negative base for an exponential function. So that negative, remember, means we have -1 times our power of 2. I'm going to factor out a -1. That's going to give me x plus 3. And then I have my plus 5. So this tells me I've got decay. So I'm going to do that y-axis reflection on my growth power of 2 points. I have a k value of 5, which means my horizontal asymptote is y equals 5. I have an h value that's the opposite now of that plus 3. So my h is a -3, which means I have a translation to the left. The plus 5 means I have a translation up. So left 3 and up 5, plus my y-axis reflection. The other thing that makes this one a little bit tricky, remember, is -1 this time is our a value. So a being negative means we also have an x-axis reflection. Okay, so what we're going to do is we are going to start with those powers of 2 points from our growth function. So we have -2 1/4, -1 1/2, 0 1, 1 2, 2 4, 3 8. And we're going to take each of those and we are going to do the y-axis reflection first. Then we'll do this x-axis reflection. And then we'll do our translations third. So other things in our key features, remember, that we can do right now: domain, set of all real numbers. And y-intercept. So we're looking at g of 0. So this, again, use the rewritten structure to make sure you get the math right. So -1 times 2 to the power of -1 times in parentheses 0 plus 3, and then followed by the plus 5. So 0 plus 3 is 3. 3 times -1 is -3. So this becomes 2 to the -3rd power. 2 to the -3rd power means 1/2 to the 3rd power, or 1 over 2 to the 3rd. So that's 1/8. And so this gives us now -1 times 1/8 plus the 5. Multiplication gives us a -1/8 plus the 5. So a couple of ways to do this one, but with our math sense, we could look at this as 5 minus 1/8. So if we have 5 wholes and we take 1/8 away, we're going to have 4 whole left and then 7/8 left. And so think of this as 4 7/8 plus 1/8 would be 4 8/8, which is 5. And think if you're not sure about your math there. So our y-intercept is 0, 4 7/8 this time. All right, we'll leave the other two until we're done with the graph. So where am I going to draw my axes? This might take a little bit of thought here because I have 2 reflections. So my x-axis reflection does mean that they are going to be below, my points are going to be below my asymptote. My asymptote is at y equals 5. So I need to make sure I can get up to 5 on the y-axis. So I'm going to put my x-axis there. 1, 2, 3. And my asymptote then will be at the top. And my points will be below that because of the x-axis reflection. Now, where am I going to put my y-axis? Well, my y-axis, remember the y-axis reflection takes like my +3 and moves it to -3. And then I have to move another 3 left, which takes that -3 to -6. So I'm going to have to get over to at least -6. So I think if I put my y-axis over here, this should work. And sometimes we blow it and we have to erase and start over, but I am thinking that probably will be okay. I'm hoping. Numbers, that's what I wanted. And I'm going to draw in my dashed line at y = 5 for my asymptote. Now, because our graph is so small, we can't be able to see where the points are going to start and do the reflections visually. We have to do it kind of more in our head. So remember that I would recommend that you do, quite honestly, you know, I said we do the y-axis reflection first and then the x-axis reflection, which is my preference if I could see everything really well, but I can't. So I'm going to probably do my x-axis reflection first, followed by my y-axis reflection, because if I have both reflections, I can do either one I want to first. That's helpful because it tells me that 3, 8 is going to flip down to 3, -8. And then it'll flip across the y-axis to -3, -8. Then it's going to move 3 more, or actually I think I'm going to go up my 5 now. So that'll be 1, 2, 3, 4, 5, left 3. And now I'm pretty sure we're going to be at -6, -3. But with something like this that's more complex, you kind of have to, keep in mind, are the points looking like you would expect them to look, that smooth curve that we're used to seeing. All right, let's try 2, 4. This one's a little easier. So 2, 4, I'm going to reflect it below to -4, flip it across y to -2, -4. Then I'm going to move it up 5. 1, 2, 3, 4, 5. Left 3. 1, 2, 3. All right. Next one. 1, 2. Flip it down. Flip it over. Move it up. 1, 2, 3, 4, 5. Left 3. 1, 2, 3. Looks like it ends up at -4, 3. 0, 1. 0, 1 does flip below for the x-axis, but it stays where it is for the y-axis. It translates up 5. 1, 2, 3, 4, 5. Left 3. 1, 2, 3. And then we have the other two. And for time, I'm going to go ahead and, well, actually, I can do that. So your -1, 1/2 is going to flip below. Then it's going to flip to the right. Then it's going to move up 5 units. 1, 2, 3, 4, 5. And left 3. 1, 2, 3. Puts it right here. And -2, 1/4 flips below. Flips to the right. Moves up 5. 1, 2, 3, 4, 5, left 3, 1, 2, 3, and ends up right there where I would expect it to. So I can draw my curve. And it's looking like I would expect it to, with that exponential curve going on towards its asymptote. So there's our g of x for this one. So now we can finish things up. So we have a range. Notice all of our points are below our asymptote, which has a y value of 5. So our range is the set of all y's such that y is less than 5. For interval notation, remember least to greatest, bottom to top. So we're going to start at -infinity and end up at the 5. And behavior on the left end where x goes to -infinity. We see the curve function is heading down. So our g of x function values are going to -infinity. We see on the right end, it's getting closer to the asymptote. So the right end is where x goes to +infinity. And so those function values which are y values, are getting closer to the y value of the asymptote, which is 5. And that finishes that one up. All right, we have a third one that is going to do powers of 10. So the only difference is that we will use primarily, I would say, these 3 key points. -1, Oh, this is the decay function. So this is not what I'm going to use. Never mind. So again, if you're really good at memorizing points, then sure, you could start here, but I'm going to start with the growth points and do the y-axis reflection again. So let's take a look at this example. So for this one, we have 1/10 and x is positive. So it tells us our base is 1/10, which tells us decay because it's between 0 and 1. So that tells me because I have a decay function, I'm going to do that y-axis reflection because I'm going to start with my growth points, which come from y equals 10 to the x. So I'm going to use my x of -1, 0, and 1. That would give me 1/10. 10 to the 0 power is 1. 10 to the first power is 10. So we'll do that y-axis reflection, and then we'll figure out other things. So the 3 is our k, so we know we've got a down 3. Translation. Our h is 0 because there's nothing added or subtracted from the x, and we have to be on the lookout. Remember that negative means our a value is -1. So we also have an x-axis reflection. So again, I would probably prefer to do my y-axis reflection followed by my x-axis reflection, but if that doesn't really work well, I can start with x and then do y, but I must do my translation last. So it will be third. That k value, remember, also gives us our horizontal asymptote number. So we got y equals k, so y equals 3 there. Our domain, set of all real numbers. Whoops, that's not what I meant. We need a less than symbol there. And our y-intercept. So y-intercept again would be where x is 0. So we're looking at g of 0. So we have a -1 times 1/10 to the 0 power plus 3. So again, exponent properties at work here, knowing that anything to the 0 power is 1. 1 times this -1 gives us -1, and then adding that to the 3 gives us a y value of 2. So our y-intercept is 0, 2. All right, we'll leave range and in behavior again till after the graph. So here, because of my x-axis reflection, I know that all of my points are going to be below my horizontal asymptote, which is y equals 3. So I'm going to move my x-axis up here, and I can get to y equals 3 up there. Then I'm looking at where am I going to put my y-axis. So I don't have any horizontal translation. So I'm just going to put my y-axis in the middle. No need really to move that anywhere. Put some numbers on here. All right. And now I'm going to draw my asymptote, which is y equals 3. Right there. Okay. So in graphing my points, I'm going to start with 110, which I can't, my grid isn't showing that particular portion of the graph. So once again, I'm going to go ahead and do my x-axis reflection first to flip it down to 1, -10. Then I'll flip it across the y-axis. Now it's at -1, -10, and then it moves down 3, 1, 2, 3. So it's actually here at -13 for y. Then I have my 0, 1. So it flips for x below. It stays where it is for the y reflection, and it moves down 3, 1, 2, 3. All right. So now, if you've been following along, have you noticed the error that I made? So remember, this is why, we've already calculated our y-intercept at 0, 2, and yet on my graph, it's showing up at 0, 4. So they don't agree. So where was the mistake? If I look at my math over here, it looks good for the y-intercept, which means it's probably in my graphing. Did you notice what direction I said my translation was? I said it was down 3, and yet k is positive. So my translation should be up 3 units. Now this is an easy fix. We'll pretend that point's not there because it's going to mess up my curve or my axis. So remember that 110, it flipped down, it flipped across. Instead of going down, it should have gone up. 1, 2, 3. It should be there. This is not one of my points. For 0, 1, it moves down for the x-axis reflection, stays where it is, and then goes up 3. 1, 2, 3. Now things are matching. 0, 2, 0, 2 for our y-intercept. And then our third point, this little -1, 1/10, which is super close to the axis, it's going to flip down for the x-axis reflection. It's going to flip to the right for the y-axis reflection. And moving it up 3, notice it's right where I would expect it to be, super close to my asymptote. There we go. Now things are looking good. So with these function situations, especially in preparation for calculus, it's always a good idea to have an idea of what to expect things to look like so that when you do make mistakes like I did, then you can catch them. All right, so here's our graph. Range now. So we can see here the points of our curve are all below our asymptote, which has a y value of 3. So we're looking at a range of the set of all y's such that y is less than 3. Again, interval notation, least to greatest is bottom to top here. So -infinity to 3. And behavior. So here we've got our left end, which is as x goes to -infinity. We see that left end is heading down, so g of x is going to -infinity. For our right end, the one getting closer to the asymptote, as it heads to the right, that means x is going to +infinity. And our function values, which are y's, are getting closer to the y value of the asymptote, and the asymptote has a y value of 3. So g of x for this end is heading towards the value of 3. All right, that finishes this up. There are a couple of questions about exponential functions here in this closure that I want to make sure that we talk about. The first is, will an exponential function always have a y-intercept? And so it's a yes or no situation, and then we have to be able to explain our reasoning for that conclusion. So y-intercepts, remember, are points that are on the y-axis, and all y-intercepts have an x value of 0. So any function will have a y-intercept if 0 is part of the domain. If 0 is in the domain, which is our x's, then there will definitely be a y-intercept. So if 0 is always in the domain, we always have a y-intercept. If 0 is sometimes in the domain, we sometimes have a y-intercept. If 0 is never in the domain, then we would never have a y-intercept. So think about your exponential functions. What is the domain of an exponential function? The set of all real numbers. That means that 0 will always be in the domain. Therefore, we will always have a y-intercept. And so that reasoning becomes our explanation. Since the domain of an exponential function is the set of all real numbers, x is part of the domain, and an exponential function will always have a y-intercept. Let's look at this other question here too. Will an exponential function always have a 0? Be able to explain our reasoning there also. So zeros, remember, are on a graph x-intercepts where the function crosses the x-axis. So if a certain type of function is guaranteed to always cross the x-axis, then it will always have a 0. If it will sometimes cross the x-axis, then it will sometimes have a 0. And if we know that type of function will never cross the x-axis, then we know that there will never be a 0. So what do we know about exponential functions and their nature as far as how the curve goes? Well, we know they have a horizontal asymptote, but that horizontal asymptote can move. We also know that we can have reflections. So like we can have an asymptote here with a curve above it. In that case, there won't be a 0, but the curve could be below it, and then we would have a 0. And so we will sometimes have a 0 for an exponential function, depending on the location of the asymptote and whether the curve is above or below that asymptote. Because another situation, let's say your asymptote is down here. Well, if your curve is above it, now you do have a 0. If your curve is below it, you do not have a 0. If your asymptote is on the x-axis, then your curve is either above that or below it. And so you can't have a 0 in that situation either. But there are a couple of situations in which you can have a 0. So we would say, will an exponential function always have a 0? No, it won't always have a 0, but it can because the horizontal asymptote can sometimes prevent the function from intersecting the x-axis. So there will sometimes be a 0, but not always. All right, that does finish up this lesson. I hope you have a wonderful, wonderful day. Bye-bye.